lecture, I'm going to discuss agriculture and drought. So basically, how drought impact agriculture and what kind of mitigation strategies we can do to minimize the impact. So this section, I'm talking about mainly use meta-analysis. Remember, we have a tutorial later on that will be rely on this same technique, so you can have a feel what it is, why people are using that. So majority of the work I'm going to talk about here is done by a former postdoc in my group, Dr. Stephanie Darianto. So when we think about agriculture, right, so we have actually a very small amount of plants we use for agriculture. Right? So we know on Earth we have almost like 200,000 flower species, many different type of plants. But when you think about agriculture, we only use a very small proportion, like 0.1% of the plants actually plant species are used for agriculture. You know, it's very actually small amount. So out of that, actually only 17 species that already account for like 90% of the food supply, right? So if you think about, you know, like one of the major staple we eat are cereal crops. Actually, the top 4 cereal crops, they already account for 70% of the food supply we actually eat every day. Anybody can guess what are the top four like cereal species we eat? Rice, yes. Wheat, yes. Millet, you mean? No, millet actually not one of the top 4. So one of them is actually heavily grown in the United States. In other places, you didn't mention corn, maize, right? So that's actually pretty large. And then the 4th one is actually barley. So that's actually the top 4 major cereal species. It's just amazing these 4 species already count for like 70% of our food supply. So just give you the idea, you know, how kind of diverse, right? It's not, the food we eat is really not diverse, right? So that's a part of the reason a lot of time we don't have a very robust response to environmental, like a drought or flooding condition. So when we think about the relationship between climate and agriculture, so on the one hand, you know, the climate condition will impact the agriculture yield, right? We have heat waves, drought conditions. Same time we could have flooding, right? So they both impact agriculture production. So at the same time, right? So when we think about agriculture, it's also a big player in terms of regulating the climate, right? We talked about yesterday. Agriculture is the largest N2O producer, right? So that is a very powerful greenhouse gas. At the same time, agriculture actually does produce other environmental consequences, right? One of them, for example, you know, for phosphorus and nitrate, so we use a lot of fertilizer in agriculture, and we tend to use a lot more than crop needs. So then leftovers, they will get into the water bodies, will actually causing the environmental issues. Right? So I guess the point is agriculture and environment, they are two-way interactions, right? So the agriculture impact environment also impact agriculture. So we have to think about these two-way interactions. So in terms of a drought, right? So we all know drought is very common meteorology phenomenon, right? It's happen any climate condition, right? So it's very hard to predict. Usually drought happens slowly and then cascaded into a big events, right? So, but that's typically how drought works. But remember, you know, we have a newer type of a concept called a flash drought. I think Vikas will talk about that, right? So it's a very fast involvement of drought. But typically drought happen very slow pace. So, you know, there are indications showing that under future warming conditions, the drought frequency and the intensity will likely increase. And also by our work, I will talk about this for next lecture. So we'll basically show you even without increase of a drought condition, the vegetation growth already become more and more water limited across the whole northern hemisphere, right? So that's tell us, you know, we have to think about water stress, have to think about drought impact. So for this talk, particularly, I'm just trying to answer two simple questions. One is how drought impact different food groups, and also how different management practice we can do to minimize the drought impact. When I talk about different crop group, I'm really referring to the FAO classifications, right? So when you think about the FAO, they classify our food into three major groups. The biggest one is the cereal, right? So the one we talk. And the second largest one is the legume group, like soybean, for example. So the third one would be anything grow underground, like a tuber or potatoes, sweet potatoes, things like that. So again, the method I'm going to use to talk about this is called a meta-analysis. So meta-analysis, in a simple word, is a statistical technique, right? So you actually don't collect data yourself from the field. You collect data from literature. So people already publish the work. You digitize the data, and then you redo the analysis for hundreds of papers. So the advantage for that, you can imagine, you can have a very quantitative way to synthesize all the published research, and you can hopefully reconcile some of the difference. This study found this impact, this study found the other impact. You can think about why that is happening, right? So there are a lot of advantage for meta-analysis. We're going to talk about in more details in our tutorial. I'll just give you an idea. That's the method we are using. So I'm going to just talk about the three groups one by one. So the first group is a legume group. So that's why with all the beans, basically they belong to legume group. Right now, basically in the western part of the world, people promote the legume as a healthy food choice, right? So because they have a high protein, and they just encourage people to eat more of them. And for legume, there are two types. One is pulses, one is non-pulses. So, but we don't need to worry about that right now. So really, we try to look at figure like this. That will be the major figure. I'm going to show several of these. So the x-axis in this one is basically the yield reduction in responding to drought. And each bar here represents one species, one crop species, like gram, right, chickpea, like soybean, groundnut, basically peanut butter, like a peanut. So, and then for each bar, for each bar, you have that is the mean value, and then the horizontal bar represents the 95 percentile, 95 confidence interval. So basically, what tell you if two species, if the bar are overlapping with each other, that means their response are not different from each other. If they are far apart, not overlapping, that means their response is different from each other. So that's basically how the figures will look like. So what we saw here is for legume group, you can see actually it's very widespread. Right? Some species are very sensitive to water reduction, to drought condition, like a black gram, that is up to almost 90% of yield reduction. Some other species like a soybean, right, groundnuts, they're like 25%, right? So it's actually much less reduction, right? So that's the first message we can get. It's just a huge spread of that. And also there is a huge difference between different species. And then we can think about why that could be the reason, right? For legume, because most of them are the natural fixers, right? So they fix nitrogen from atmosphere, right? Working with the bacteria. So there are two types of this natural fixer relationship. One is called interminate, one is called determinate. So the major difference is really the relationship between roots and the root nodule. How do they actually associate with each other? So for the determinate, so the major feature for this is the root nodule actually grow outside the roots. So that means if plants are under water stress, so the root nodule can detach themselves and just detach from the roots. So we think because of this, that's why for species like green gram, black gram, for this type of species, for determinate, so they are the group actually are very sensitive to drought condition, right? So that's our thinking for this sensitivity. But for soybean, remember this one also belongs to this group, but soybean is actually not that bad. Actually, the reduction is much less, right? So that's part of the reason we think for soybean, for example, wheat, for other like major species people eat every day, people have already been through so many generations of a genetic like breeding, modification, a lot of things actually try to improve their drought resistance. So then what we look next is a phenology stage. Basically, when was the drought timing, right? So drought could happen, for example, in early stage of a plant growth, but could happen in late stage of a plant growth, right? So the message here is, you can say for early stage, the yield reduction is quite small, but for late stage, for reproduction stage, the yield reduction is much higher, right? So that's not something surprising, right? Most of farmers probably know, right? So if the drought condition happen in the flowering or even later stage, that's very bad for plants, right? So you have to take actions for that. And then we also look at the soil texture impact, right? So because we know some soil are sandier, some soil are clayish, and we want to look at how the soil texture affect the yield response. So what we found here is for coarser soil, actually, and even fine soil, their reduction is actually not that bad. But for medium soil texture, the reduction is much bigger. So that's is kind of counterintuitive, right? Because we know medium soil texture is actually good for plants to grow. But here, what we show is even it's good for plant growth, but if you have a drought condition, it's actually very bad for plant growth. So that is the legume group, and then the next group, this is the biggest group for our food production. That is the cereal, right? So like I mentioned, like corn, like wheat, and they all like belong to the cereal group. So different from legume. Legume has many different families getting together. For cereal group, all of them come from one family. Is very few families, all like a grass, right? So that's why they are for grass. For their inherent nature is a grass family. They have a much deeper roots, right? So that means they're already like a drought resistant compared to many other different species. And so that's what we saw here, right? So in general, you can say first thing is for cereal, right? So their spread is much smaller, right? It's a very narrow range, except anaerobic rice. That's why it's all over the place. But for others, you can say it's actually much narrower range. So, and also the rate of production is much smaller, right? So it's like a 35%-ish. So that is another key message for this. So for cereal, because we have so much data in the literature, besides the yield reduction, we can also look at their drought sensitivity. So what I mean drought sensitivity is the x-axis is basically the degree of water reduction. The y-axis is the yield reduction, right? So I can do that for all the species. I can take the slope of each species, and then I can put them together. So that's give you how sensitive for each species are responding to drought. So there are differences in drought sensitivity, but what I highlight here is the difference between wheat species and maize and corn, right? You can see here, maize is actually much more sensitive compared to wheat, much more sensitive to drought, right? So that's in a way is also counterintuitive, because we know maize, they are C4 plants. They are using water very efficiently. Water use efficiency is quite high for maize. But then what we saw here is, but they are very sensitive to drought condition. Even they are very high, even they have a very high water use efficiency, right? So basically what they tell us is water use efficiency and drought resistance or drought tolerance is not the same thing. Right? Even some crops, they are water use efficient, they could be very sensitive to drought condition. Right? So that kind of thing is counterintuitive, but sometimes it's only emerge if you actually use a very large amount of data set to be able to do that. And the last group we look at is called the tuber. Tuber essentially refer to all the species grow underground, right? Like sweet potato, or cassava, like here. Right? So the idea is, some cultures, they actually rely on a lot of the food on the tuber group, right? In some country in Africa, right? So they actually rely on cassava quite a bit. So for them, what we can see here is they are quite sensitive to water, right? So the reduction is 60%-ish, quite high. But also, one interesting thing is for tuber species, we were able to look at the drought sensitivity for both tomato and sweet potato. These are the drought sensitivity when we put them together. So basically, what we saw here is for sweet potato, the drought sensitivity is actually much bigger than potato. So again, when you talk with farmers, it could be counterintuitive. People always think sweet potato are hardy plants, right? When you grow them, people tend to think sweet potato are much more drought resistant. So, but here what we saw, what our results actually tell us is sweet potato probably is a hardy plant in terms of survival. They don't die if you have a drought condition, but doesn't mean they will produce food, right? So basically it means their survival is pretty strong, but they don't really have a high yield potential if you have a drought condition, right? So that is a kind of a key message for this comparison. So I guess overall, really, when we put all three major groups together, right? So really, the message is, there are very big variation in terms of different group, different species respond to drought conditions. Some species are very sensitive, some are okay, right? So some are in between, right? Also, like I mentioned, one of the major difference between these groups, some reason is a kind of a inherent nature of the plants. For example, cereal species are grasses. They tend to be drought resistant in the first place, but also because they have deeper roots. But also, for a lot of the cereal species like maize, wheat, and also some legume species like soybean, right? So they have a lot of genetic modification has been done to them, so they are becoming less sensitive to drought. So that's both play a role. So to summarize this part, basically what the ones already talked about, really we talk about like cereal. They are the most robust among all three groups in terms of drought resistance. So that's related to their inherent property, but also related to how many research, how many studies has been done for this group. And we talk about in terms of drought timing, right? So in terms of the soil texture. So if you have a medium soil texture, so that is good for plant growth in general, but that doesn't mean it help with the drought, right? So if you have a drought condition, medium soil texture tend to have a highest yield reduction. And also drought timing matters, right? So if you have a drought happen in the early stage, in vegetative stage, maybe that's okay. But if you have a drought happen in the later stage, you have to take action quickly to avoid the big loss. And also by comparing maize and wheat, so basically what we show here, water use efficiency doesn't mean drought resistance. They actually are different things. We can't really use them interchangeably. And also by comparing sweet potato and potato. So basically what we show here is for drought resistant plants, sometimes people call them like a sweet potato. Doesn't mean, usually they mean that's their survival capacity. They don't die, but doesn't mean they can still produce yield very well. So what we should do, right, to keep improving the drought tolerance or resistance? So one thing, of course, we can continue doing the plant breeding, right? So we can already saw the impact for cereal and some of the legume species is very effective. But also there are some agricultural practice you can do, right? So I will talk about a couple of them, give you example. Like one is mulching, one is no-till. So mulching is a practice people use quite a bit in dryland agriculture. Right? So it was first started in the United States for mulching technique, but right now the technique is more widely used in China, in western part of China. So basically you have a plastic cover the soil surface, and then you make ridges and valleys, right? So you make a hole and you plant crop here, typically like maize or corn, right? So what happens is when you have rainfall events, the water actually will run down to the hole, will get into the hole, right? So plant can use, and then the cover actually reduce evaporation, right? So that is a very effective water saving technology. So we did a meta-analysis, try to look at how effective this practice compared to irrigation. So we look at, you don't need to, there are different types of mulch, right? You can use plastic, you can use like a straw, we don't need to worry. Let's just look at the top two. So that is the irrigated treatment, and then you have plastic mulching. And we look at soil moisture change, yield change, water use efficiency change, and also ET. So really the key message you can see here is, if you compare the soil moisture between mulching treatment and the irrigation treatment, they are almost the same, right? So, and also when you look at the yield, they're almost the same as well, right? So basically, without any irrigation, the plastic mulching can produce the same yield as the irrigated crops. And then when you look at the ET part, you can see actually irrigated part has a very big ET loss, and the plastic mulching part has a very small one. So as a result, that's why water use efficiency is much higher for plastic mulching, right? So because water use efficiency, you use yield divided by ET, right? So, that's basically tell us, from the water perspective, the mulching treatment is very effective. It actually can produce the same amount of crop yield without using much water at all, right? Without any irrigation in this case. But the problem for plastic mulching, of course, is an environmental concern, right? So because you tend to left a lot of the plastic in the field, that's actually in the long term is not necessarily a good thing. So the second practice I'm going to discuss is called no-till, no-tillage. So it's been promoted as a conservation practice. So essentially, you don't really plow the soil after harvesting. You just left all the residue on the ground, and this is a traditional tillage. And this one, because you have the crop residue cover on the ground, that's reduce evaporation, right? So reduce water loss. So that will be very helpful for plant in terms of the water use. So, but the problem for no-till, for example, one of the things people found is no-till actually can induce increase in N2O emission, right? So because if you have a very good soil moisture condition, and also you have a lot of residue on the soil surface, right? You have has a lot of nitrogen there, right? So you introduce a lot of the N2O emission. But we don't know. But what we don't know is really how no-till will change the water quality, like the nitrate leaching and other nutrient leaching. So in literature, the results is kind of mixed. Some found no impact, some found reduction, some found increase, right? So that's why we want to look at this through a meta-analysis point of view, try to look at what's the consensus is, what is the overall conclusion for this. So before I talk about the results using meta-analysis, I will talk about how no-till actually changes soil property and how that related to the nutrient leaching, right? So first off, if you have a no-till, means you have a plant residue on the soil cover, right? So that means you tend to physically block the water flow, right? So that means you reduce the surface runoff, right? But at the same time, if you do no-till for a very long time, soil will be compacted. So that means water not easy to infiltrate inside the soil, right? So the soil compaction actually will introduce to like a increase runoff. So no-till could either reduce runoff or increase runoff, depends on how long the practice is, depends on particular situation. So that's one impact on no-till, on nutrients. Another is because you have a soil organic matter, right, on the soil surface. So basically that means you add a lot of potential nutrients. So that means the concentration from the runoff very likely will increase. And also the leaching is vertical. The concentration of both runoff and the leaching likely increase just because you have a lot of the organic matter on the surface. And also no-till tend to create a lot of the micropores in soil. So the micropores can make the water flow much easier, right? So that means the leaching, the volume of water from no-till could be bigger. So then when you think about the environmental consequence of a no-till, you have to consider all of them, and then what is the net impact of a no-till, right? Then we can take a look for the nutrient impact separately. First, we look at the nitrate, and then we look at the phosphorus. So for each nutrient species, I'm looking at both concentration and also load. Load is basically the product of a concentration and the volume, right? So because that is really the total amount of nutrients coming out of agricultural field. So this is more meaningful. But we still use concentration because some farmers or some research, they only report concentration. That's the only information you have. So we still use them. So again, that's the same kind of a layout. So the x-axis basically tell you the changes in concentration. And so if you have we have a zero line here, right? So if you have this 95 confidence interval, if this one overlap with the zero line, that means statistically there's no treatment effect, there's no change like this. But if this one is on the right side, that means your concentration is increasing, right? If on the left side, means concentration is decreasing, right? So basically what we saw here is in terms of concentration, no-till does increase the surface concentration for nitrate, right? So that makes sense. Like I mentioned, if you have a crop residue on the soil cover, right? So they actually will add organic nitrogen, and they will mineralize, become nitrate, right? So the concentration is increasing. But for leaching, we didn't actually say the concentration is the same between no-till and the conventional tillage. And then when we look at the load, right? So that's different. You can say load is actually there is overlapping with zero. That means for nitrate, the load is actually the same between conventional tillage and the no-till. So what that means, but we know concentration is higher, right? That means the volume, the runoff volume is actually smaller. That's why when you make the product, the total is actually not changing. So that's what tells us about the total runoff for nitrate. And then when we look at the leaching, right, the concentration didn't change much, but actually the load is actually significantly higher under no-till compared to conventional tillage. So, but the concentration didn't change. That means must be the volume directly like increasing. So then the end product means the load is increasing, right? So I guess the summary for that is sometimes you can see the difference between concentration and load results, and preferably this one is preferred because this is actually telling you the actual total amount of nutrients coming out of the agricultural field. So concentration just a part of the story, not the full story. Load is the full story, right? So because load has both concentration information and also volume information. So that's for nitrate. So the next one will be for phosphorus. So phosphorus, there are different forms of phosphorus. You could have a total phosphorus, you could have a particulate phosphorus, but also you can have a dissolved phosphorus. So we look at them separately. So, but we also look at concentration and load separately. So you can see in terms of concentration, right? So the total P and the particulate phosphorus, they actually has a lower concentration under the no-till treatment, right? So that makes sense because the no-till physically really blocks the total phosphorus. But for concentration, actually we saw for dissolved phosphorus is actually much higher. So that means you have a residue, they actually adding the dissolved phosphorus. So the concentration is actually higher under no-till treatment. So that is the concentration. So for total load, that's actually almost the same as the concentration. You can see total phosphorus and the particulate phosphorus, the total load is actually much lower under no-till treatment. But for dissolved phosphorus, the load is much higher under no-till. But remember when we talk about the water issue, right? If you think about eutrophication in lakes, for example, so the most important source is actually dissolved phosphorus. So no-till increasing the load of a dissolved phosphorus means that's not good, right? So that means you potentially can introduce the eutrophication problem, right? So, but that's basically tell you, for both phosphorus and the nitrate, so no-till actually has the potential to increase the loss from agricultural field. So after this, we then take a look how kind of different climate condition and the different water condition, how that will change the phosphorus or nitrogen loss through the agricultural field. So here basically what we did is we classified the agricultural field into like a dryland region and a non-dryland region. So what we saw here, you can see for both on the top is the nitrate, bottom is the phosphorus. So you can see for they almost similar, right? So for concentration, you can see dryland is actually has a much higher concentration under no-till compared to conventional till. And the load also similar, like under dryland conditions, there are much bigger load, bigger both nitrogen and phosphorus loss through agricultural field, right? So that's one thing. Basically, the geographic region impact, right? So if you have a drier region or lower or wetter region, basically what we saw here is a drier region, the issue is much more severe. So, and then we can look at one region and then look at wetter period and drier period, right? So what we saw here is, if for one particular location, when you say wet year or normal year or dry year, regardless the concentration or load of phosphorus, nitrogen and phosphorus, you can see actually the drier years, they tend to be higher, especially for load, right? So basically for both dryland and also for drier years, the nutrient loss will be much bigger, right? So that's basically the results tell us. So really what that means is we know there is a potential for higher nutrient loss from the no-till field, right? So that impact is much higher under dryland or water limited environment or under dry years, right? So the implication for that is, as we all know, if you think about the future climate predictions, a lot of time the dryland become drier, and also some other places they tend to have a higher frequency of drought condition. So that means the nutrient loss issue will become more severe in the future. So that's basically the implication of such results. So to summarize this part, really what we talk about is when you think about the nutrient loss from agricultural field, sometimes people use concentration, sometimes people use load, but actually you can't use them changeably. They don't always tell you the same answer, right? So, and preferably we want to use load because that is a more accurate representation of nutrient loss through agricultural field, because it's not only considered the concentration, it's also considered how much water get lost, right? So based on this study, basically what we show here is for no-till practice, no-till is pretty good for reduce soil erosion for other things, but for water quality part, it's really has a very limited could be not even like positive, it's actually negative impact, right? We talk about dissolved phosphorus and nitrate loss are much higher under no-till condition, right? Especially under drier conditions. So, that's basically lead to like even higher nutrient potential loss under future climate conditions, right? So that's basically prompt us to think about then what's next, right? So what additional things we can do to minimize the no-till impact, right? So one of the things we can think of is basically adding additional agricultural practice to minimize the impact. So traditionally when people doing the no-till, when they harvest the plants, they left the residue on the ground, but it's basically nothing else. So that's why a lot of time nutrients get lost to the groundwater, to the surface runoff. But if you actually, instead of keeping the ground fallow, one thing you could do is actually you're adding the cover crops during the fallow season, right? So that actually can take up the nutrients, can actually reduce the nutrient loss, right? So that would be a better way, in addition to no-till, right, to help with the environmental conditions. So that's basically kind of is a new perspective I wrote this year. So basically think about drought in agriculture and what kind of the strategies you can do to minimize the impact. So the key figure for this one is this one, right? So we discussed, there are many long-term strategies you can use. You can build in reservoirs. You can, make terraces, like make the place more water use efficient. But this one are good, but they are very costly and very like a long-term oriented. But there are many things like a no-till cover crop. They are like a much smaller scale implementation is possible. It's very much cheaper. So that's kind of things we should be focused on, right? So that's what we talk about. You can modify the soil, right? So that's the kind of yellowish color, but you can also change the crop. That's a green color, but you can also change the water. Right? There are many different ways you can do, right? So they can be responsible for maybe like a seasonal drought. Some could be responsible for like mitigate the impact for flash drought. Some may be responsible for like a long-term drought. So that's kind of just a kind of a summary about the thinking. What kind of different practice you can do. How do you put them into different categories in terms of soil condition, plant condition, water condition, and how that impact the different time scale of drought. Some is long-term drought, some is short-term drought. And in the middle, we gave kind of the mechanism, right? Why this drought mitigation strategy works, right? So some we know because of they change soil condition, some we know the changing plant condition, some is basically like water condition, some is combined with the soil condition and water condition, right? So yeah, hopefully you have a chance, you can take read the perspective, think about that. So I guess really, just a quick summary of all today's talk, all the first part, the first lecture. So really, when I talk about, when we think about the agricultural production, they are really threatened by the climate variability, especially drought condition, right? So that is actually very significant factors. But the impact is different for different crops, different crop groups. And also, we emphasize here is some of the practice people use to mitigate the drought is actually could have a kind of unintentional consequence, like a no-till only no-till, right? So that one could actually impact water quality, right? So you have to think about additional ways to minimize the impact. So that's why we talk about you have to think about synergy from multiple practice. You integrate them, and then like no-till plus cover crop, put them together. So that's that way you can actually reduce the impact of drought on agriculture. So I think that's all for this part of lecture. Like I mentioned, the majority of the work is done by my former postdoc, Stephanie Darianto. But also I want to acknowledge all the work from earlier former groups, including Vikas. He stayed in my group for about a year. So yeah, I guess thank you guys. I'm happy to answer any questions, or if you have anything not clear, you want me to elaborate or clarify, I'm happy to do that. Thank you. So any questions, comments? So again, the analytical method we are using is a meta-analysis, right? So that's the ones I'm going to talk about in more details. You actually have a hands-on exercise yourself and do that. So that's basically you can generate things like this, right? So this one is good. Is a synthesis of hundreds of papers, give you a very quantitative information. So I guess any questions for this? I know it's probably new for most of you. You probably never done anything yourself on this, right? So if you have questions, feel free to ask. But also you can save that for the tutorial as well. Okay, I guess if no questions, we'll just take a break from now. For now, I guess whatever I was told I will continue the next. I will start the next one. We'll just take a break for now. And if you have a question, feel free to come to me to ask separately. All right, thank you guys.